Yeah, so my name is Chris Davis, and I'm going to be talking about solar energy technologies, trying to maximize the efficiency, but not just that, also like the reliability over time. So with photovoltaic modules, you need them to operate in the field in harsh conditions for 25 to 30 years. So that's an important piece, and those both tie into the affordability. The more efficient and the more reliable you can make these technologies, and if you can do that in a way that's very cost effective in terms of the manufacturing processes used, that can make solar energy more competitive with other energy technologies. So I'm an assistant professor in material science and engineering. I'm also affiliated with the RISES cluster and the Florida Solar Energy Center, as well as CREOL, the College of Optics and Photonics. So in terms of a research and teaching overview, my research group is focused on photovoltaic materials and devices. So we're looking at semiconductor devices that can maximize the conversion of sunlight into electricity. And so that relates to photon management, dealing with light matter interactions to collect as many photons as possible, maximizing the charge carrier generation and separation, and the extraction of those charge carriers, and then delivery of that current and voltage to an external circuit. So our group works both on the device and the material level with a lot of that. And my team, I have 2 postdocs currently, 5 graduate students, and about 12 undergraduate students. In terms of courses taught, I've taught a structure and properties course at the undergraduate level. Most of my teaching is at the graduate level. I have a course in photovoltaics that I'm teaching right now, actually, as well as courses related to optical properties, electrical properties, and optoelectronic materials for different applications. Some accomplishments I'll mention briefly. I'm currently a PI on 4 projects funded by the U.S. Department of Energy. 2 of which are kind of large multi-year projects. And then also my team has been publishing quite a bit. So we have just thus far this year, we've had 11 peer-reviewed journal publications so far. I'm also on the PV device committee for IEEE's Electron Device Society, and a peer reviewer for the Department of Energy, as well as national labs and other journals. So, goals and motivation. Why am I interested in photovoltaics? Well, PV is a clean, reliable, inexpensive energy source, and you can see that just based on the incredible growth that the PV industry has been able to sustain over a long period of time. I do think it's an important piece of the puzzle to address climate change, and it's also just a great driver of economic growth. I'm excited about it because the industry is growing strong, but I still think there's a lot of room for technological improvements. And so you can see this chart, the growth. You can see, back in kind of the mid-2000s, Germany developed what's called a feed-in tariff program. Basically, the federal government incentivized people to install photovoltaic systems. And a lot of that growth early on in the industry was really just in Germany, primarily. And so what you've seen in the last few years is now there's these new markets that are growing at an even faster rate. So right now it's really China, the US, and Japan, the big markets for photovoltaics, but also a lot of other places around the world. So although Germany's still a big piece of that, and we owe a lot to them for that, now it's really, just a global industry. It's already over $100 billion a year industry, expected to grow over 300 billion just within 10 years. There's like something on the order of 250,000 people that work in the PV industry, just here in the United States alone. So that's exciting. And I think there's a lot of opportunities to do research to help the industry, but also to kind of train the workforce for this growing industry as well. And so one of my main goals is to try and help make UCF the top university for research in industrially relevant photovoltaics. So I'll talk about some of the current research topics around photovoltaics that my group is working on. So one is this idea of passivating carrier selective contacts. So typically solar cells are made in a similar way as things like transistors, where you have diffusion processes to form a doped p-n junction. One of the challenges with those specific technologies is that when you then go and put metal contacts directly onto the actual semiconductor, you have a lot of charge carrier recombination. So you can think of these as defects that gobble up charge carriers that you're trying to use to generate current and voltage within the device. So one approach to alleviate that is to do something where you actually, instead of putting the metal in direct contact with a semiconductor, you have very thin kind of passivating insulator layers that you can still get tunneling of charge carriers through. And then you put something called a carrier selective material that can actually separate charge carriers. So the idea is you can think of it as like a sandwich in the solar cell, one that collects the positive charge carriers, the holes, one that collects the negative charge carriers, the electrons. So if you combine that high quality passivation, so passivating these interface defects that prevents recombination, and then excellent carrier selectivity, you can really elevate the ceiling in terms of the maximum efficiency you can provide for a solar cell. So that's the general concept. So I currently have 2 projects funded in this area with 3 more proposals that are pending. I have some collaborators here at UCF on this topic, Professor Banerjee in MSc and also with the React cluster, Professor Chitel Yurka in chemistry, also in the React cluster, also Professor Kumar and Professor Carr. We have an active project where we're looking at doing printing of different materials for these types of devices, and also Professor Kushima, who's helped a lot with some of the TM imaging that we've done for some of these things. I also have a lot of external collaborators, Fraunhofer ISA, Schmid Group, BNIC, Australian National University, UC Berkeley, and University of Melbourne. And to give you an idea of some of the different flavors of these passivating carrier selective contacts, one thing that we looked at is using atomic layer deposition, which is a process that in particular, Professor Banerjee and Professor Yurka's groups are really effective at doing this. So we've looked at, using aluminum oxide, like only 1 nanometer, 1.5 nanometer of aluminum oxide to passivate the surface states at the silicon wafer. And then we can basically get tunneling through these layers into the contact there. So we published that. We found that worked pretty effectively, although when you put metal directly onto that aluminum oxide layer, you can only use that really as a effective back contact because you're covering the whole surface with metal. So we're also looking at layers that you can put on the front to replace the metal that can be hole selective. So we just published something recently in Advanced Materials Interfaces where we're looking at a high throughput, what's called a spatial atomic layer deposition of a material called molybdenum oxide that essentially really supplies effective band bending to prevent electrons from moving to the contact. So that we're pretty excited about those developments. And then just recently we got on the cover of PSSA with some work looking at hydrogenated aluminum oxide, moly oxide kind of film stack that we're now coupling with transparent conductive oxides that can be used on the front side of a solar cell. And that work's been done in collaboration again with Professor Banerjee and Professor Yurka. More recently, I have a graduate student that's working with Schmid Group. They're a large equipment manufacturer on an atmospheric pressure-based chemical vapor deposition process to deposit doped polysilicon. So in this case, we have a very thin silicon oxide layer that you can just grow chemically very easily in manufacturing. And then this atmospheric pressure thin film process, it doesn't require vacuums, very high throughput. And so this technology is of interest to a lot of companies right now. So we're pretty excited about that and just wrapping up a journal paper on this. Another area of research that I'm working on right now is something called spatially resolved characterization. So one thing to keep in mind is these devices, unlike transistors and things like that, these are large area devices. It's basically one big diode, 6-inch by 6-inch square. And so you can also have very small defects on the order of anywhere from nanometers, microns to millimeters that can have a big impact on the overall performance. So one of the things that we do is we use innovative measurement techniques like photoluminescence and electroluminescence imaging, where either we shine light on the solar cell or pump current into the solar cell and look at how it re-radiates light of a different wavelength. And that luminescence at each pixel, we can attribute using some different calibration techniques to a specific voltage. And so what we do is we treat every pixel as kind of like a parallel connected diode within the solar cell. And then we can solve for these different circuit parameters that typically you only measure at the solar cell level. So I've given some examples here of what we can do with this photoluminescence imaging, where we can create images of the efficiency of a solar cell, which is great. But more importantly, we can look at things like the series resistance. So you can look at specific defects. So you can see these bright regions have a high series resistance. That's because there's an interruption in the contact grid. And you can see that it shows up in the series resistance, and also it shows up as a dark area in the efficiency. So you can kind of quantify the penalty that these defects are causing, and also kind of figure out what the root cause of the defect is. This is kind of the first step towards that analysis. So here's something else called the J0, which is related to recombination. And these kind of grain boundaries and things like that, and dislocation centers act as recombination centers. So that also is it. So this has been an interesting area of research. We get a lot of samples from industry, from manufacturers that are like, just wanting to know what went wrong with certain batches. So maybe it's a new product line that they're developing, or maybe it's just something right off their high volume manufacturing process, but they're trying to figure out what really happened. And so this is an important first step to get there. And some recent research that we've been working on too is something called multiscale characterization. So this is an entire PV module, right? So this is like a 3 foot by 5 foot type of module. And you can see we're collecting electroluminescence images at different exposure times as it's exposed to damp heat. And there's a specific corrosion mechanism that affects the series resistance that we start to see here, these dark regions. And so we have a collaboration with Case Western Reserve University where they're doing a lot of these exposures. They send us the samples. We'll do all this kind of large scale characterization of the panels, but then we'll actually look at these dark and bright regions, core out regions within the actual solar panel. So you can see the aluminum frame, the polymer backsheet and everything. We'll core that out, and then we'll go and do different materials characterization steps to try and really understand what's going on. And so here what we found is we see some migration of tin coming to the interconnect that gets oxidized. It results in a delamination of the grid line, which results in a loss of current transport, between the device and the metal contact. So this is an area that I'm really excited about. We have one project currently funded through Case Western Reserve University. We're a subcontractor on that, but we have another one that's pending right now that we're really excited about. And I've done a lot of this work with Hubert Senior at FSEC, as well as Professor Yurka and Professor Seal at UCF. In terms of next term plans, some of the things that I'm interested in moving forward, I'd like to continue this work in these carrier selective materials, apply them to other semiconductors outside of just silicon, not just for photovoltaics, but also there's applicability in light emitting diode, photodetectors, sensors, anywhere where you're trying to engineer light matter interactions and limit inefficiencies in the charge carrier extraction or injection process. So currently, as I said, I have 2 proposals pending and 2 more planned in this area. I'm also continuing work to expand the multiscale characterization in collaboration with some of these people that I mentioned before, with 1 proposal pending. I'm also working right now with Professor Mubarak Shah, as well as Hubert Senior and some industry partners to apply computer vision and machine learning to these luminescence images. I give an example here where we have a solar cell that has some cracks and some contact defects. So we're working now to have a team of 8 undergraduate researchers that we've trained how to annotate these images. So we're doing like a supervised machine learning so we can kind of predict this. This is of strong interest right now to industry. And then another area that I'm really interested in working in is trying to do things like enhance grid resilience during things like extreme weather events by having reliable PV modules and systems designs. There's a lot of work going on at using PV coupled with batteries to basically help make the grid more resilient. But I'm interested in making sure that if you do that, the photovoltaic modules and system designs you use are going to be able to handle whether it's, a hurricane, flooding, situations like that. So I'm planning something right now and working with Thomas Wall in civil engineering in the coastal cluster, as well as Professor Dimitrovsky in electrical engineering at Rises. And then longer term, I have some work that I've been doing. I sent a graduate student up to Brookhaven National Labs to do this self-assembled nanostructure growth of oxides using ALD. So we're able to grow different shapes of oxides. And so what we're really interested in, a lot of groups have done things like this for just manipulating light matter interactions. So things like optical metamaterials. The thing I'm interested in is more multifunctional nanostructured oxides. So where they have both the optical and electronic functionality. So this is, again, especially relevant to things like solar cells, photodetectors, LEDs, lasers, anything where there's both you have to worry about both photons as well as charge carriers. I'm also interested in doing spectral luminescence imaging to actually create not only images of the things I showed before, but actually images of the quantum efficiency of a solar cell or photodetector. With an industry partner, we're looking at that. I'm very interested in bigger picture issues, trying to maximize the benefits of photovoltaics beyond just providing clean, low-cost electricity, but looking at other societal problems or just industry problems where photovoltaics can play a role, trying to target interdisciplinary projects with kind of this larger potential impact. So I'm very much interested in that. And then finally, I'll leave with just creating unique training opportunities for undergraduate engineering students. I think Lockheed Martin's program that Tom was just talking about is kind of the gold standard for that. I think we should try and do more of that in every possible sector we can. And I think UCF's PV research infrastructure, I think there are ways to create, a much smaller program, but centered around photovoltaics to give particularly undergraduate engineering students unique opportunities. And that could be in photovoltaics, but also other semiconductor-based industries. So that's something I've been talking about with some other faculty members that I'm highly interested in.